Imagine everything you know, every atom, every force, every interaction, boiled down to one single idea: tiny vibrating strings. This is the core of string theory, one of the most ambitious and mysterious ideas in modern physics. At its heart, string theory suggests that the fundamental building blocks of the universe are not particles like electrons or quarks, but minuscule, one-dimensional strings. These strings vibrate at different frequencies, and their vibrations determine the properties of what we perceive as particles. In other words, the universe isn't made of dots, it's made of music. The idea sounds wild, almost poetic, but it's grounded in real physics, a desperate attempt to unify the two biggest and most successful theories in science: general relativity, which explains gravity and the large-scale structure of the universe, and quantum mechanics, which explains the tiniest particles and forces. The problem? These two theories don't get along. In extreme situations, like inside black holes or during the Big Bang, they break down. The math explodes. The models collapse. Physicists call this the incompatibility problem, and for decades it's been the greatest puzzle in science. Enter string theory. It promises to unify all fundamental forces, including gravity, into a single framework. A theory of everything. But there's a twist. For the math to work, string theory doesn't just require the 3 dimensions we live in, or even 4 with time. It needs 10 dimensions. And some versions even suggest 11. So where are these extra dimensions? Why don't we see them? Physicists believe they're curled up, infinitely small and hidden, within the fabric of reality itself, like tiny loops folded into every point in space. We don't notice them because they're smaller than anything we can detect. But if they're real, they might explain everything from the behavior of subatomic particles to the birth of the cosmos. So what would it mean if reality is just vibrating strings in a multiverse of hidden dimensions? Let's take a closer look. If string theory is correct, then everything, light, gravity, time, even you, is the result of vibrations. Just like different notes on a guitar string create different sounds, the various particles in the universe are notes played by tiny vibrating strings. It's a radical shift in how we understand reality. We're not made of building blocks, we're made of harmonies. But the implications go even deeper. String theory naturally leads to the idea of the multiverse, the possibility that our universe is just one of many. Each universe could have different physical laws, different particles, even different dimensions. In some, gravity might be stronger. In others, time could flow differently, or not at all. And here's where it gets even stranger. To connect these strings and dimensions, string theory proposes objects called branes, short for membranes. These are multidimensional surfaces that strings can attach to or move across. Some theories suggest our entire universe might exist on a brane, floating in a higher dimensional space. If that's true, then what we think of as the universe could be just a thin slice of a much larger reality. So, how do we test this? That's the big problem. Right now, string theory is incredibly elegant, but also incredibly hard to prove. The strings are so small, on the scale of the Planck length, a billionth of a billionth of a billionth of a centimeter, that we can't detect them directly. And the extra dimensions? We've never seen them. Some critics argue that if a theory can't be tested, it doesn't belong in science. Others believe it's just a matter of time. That new technology, or perhaps mathematical breakthroughs, will eventually give us a way in. Still, string theory has already changed the game. It's reshaped how we think about space, time, and reality itself. It's inspired new branches of physics, and even offered tools to study black holes and quantum gravity. But maybe the most important thing about string theory is this. It reminds us that the universe might be far stranger, deeper, and more beautiful than we ever imagined. A place where physics meets poetry, and where reality might just be music. So the next time you hear a song, or feel the resonance of sound in your chest, remember, you too are a symphony. And somewhere, deep in the quantum fabric of the cosmos, the strings are still playing. But what if this music, the vibrations of strings, isn't just a metaphor? What if it's the literal foundation of reality? That's what string theory proposes, that everything in the universe is made of unimaginably tiny, vibrating strings of energy. These strings aren't like violin strings or rubber bands. They exist in a space so small, 1035 meters, it makes atoms look like planets by comparison. And each type of vibration corresponds to a different particle. One pattern creates an electron, another becomes a photon. A third becomes a graviton, the theoretical particle that carries gravity. This idea is revolutionary because it unifies everything. For the first time, gravity, the force that rules the large-scale universe, and quantum mechanics, the laws that govern atoms and particles, can be explained by a single framework. And it gets stranger still. For string theory to work mathematically, it requires extra dimensions, 1, 10 or even 11 total. We're used to 3 dimensions of space, plus 1 of time. But according to string theory, there are more. These extra dimensions are compactified, curled up into shapes so small we don't notice them, like threads woven into the fabric of reality. Picture an ant walking on a tightrope. To us, the rope looks like a one-dimensional line. But to the ant, it has width, curvature, depth. Some theorists believe that inside these extra dimensions lies the answer to many of physics' deepest questions. Why do particles have the masses they do? Why does the universe contain matter and not antimatter? Why do the laws of physics seem so fine-tuned for life? And then there's the pet landscape problem. String theory doesn't predict just one universe. It allows for 500 possible universes, each with different properties. Some with no atoms, some with no stars. Some collapsing in milliseconds, but a few, like ours, could support life. If true, this means we live in a multiverse, a cosmic lottery where our universe just happened to draw the right numbers. But that raises a chilling thought. What if our universe isn't special? What if it's just one of many? This also changes how we might think about reality. If we live on a 3-dimensional brain floating in a higher dimensional space, then other brains, other universes, could be floating nearby. We might never see them, never reach them, but they could bump into ours, or even spark new Big Bangs. Some physicists believe this could explain the origin of our universe, a cosmic collision between brains. So is string theory science or science fiction? That's the controversy. Right now, we can't test it. The energy required to probe the string scale is trillions of times higher than what the Large Hadron Collider can reach. And the extra dimensions are too small to detect directly. Critics say this makes string theory unfalsifiable. But defenders argue that it's our best hope for a theory of everything, a unified description of all fundamental forces. And here's the twist. String theory didn't start with a quest for truth. It began as a failed model for the strong nuclear force, but its math was too beautiful to ignore. Physicists kept digging and found it matched the quantum world and general relativity. It wasn't what they were looking for, but it might be what they needed. So where do we go from here? Some researchers are developing string-inspired models to explain black hole entropy, cosmic inflation, and even dark energy. Others are exploring M-theory, a broader framework that unites multiple string theories using 11 dimensions and a new type of object, the membrane. In this view, strings are just one-dimensional slices of a deeper, richer structure. And then there's the possibility that reality itself might be holographic, that our 3D universe is just a projection of information stored on a 2D surface, like the image on a screen. This idea, supported by some string theory models, is now being explored to understand black holes, information paradoxes, and even the nature of consciousness. In the end, string theory invites us to imagine a universe built not from things, but from tones, not from particles, but from patterns, a cosmic symphony playing across dimensions we can't yet perceive. And maybe that's the most powerful idea of all, that the closer we look, the more the universe seems less like a machine and more like a masterpiece. As we delve deeper into string theory, we encounter a realm where mathematics and metaphysics begin to blur. One of the most fascinating implications of the theory is the potential unification of all forces. Gravity, electromagnetism, the strong and weak nuclear forces, under a single framework. This idea has been the holy grail of physics for over a century. Einstein spent the last years of his life searching for such a unified field theory. String theory might finally be the answer he never found. But this unification doesn't come without complexity. The mathematics of string theory is incredibly dense and abstract, relying on concepts like Calabi-Yau manifolds, six-dimensional shapes curled up within the extra dimensions of space. These manifolds aren't just theoretical decoration. The exact shape of them determines the physical laws in our universe. They dictate how particles interact, how forces behave, and what kinds of matter can exist. It's as if the geometry of hidden dimensions acts as the software code for reality. And here, another mystery emerges. Why this configuration? Why this set of dimensions, this mathematical structure, this universe? This leads us to the concept of the string landscape, a vast space of possible universes, each one defined by a different configuration of the extra dimensions. Some physicists estimate the number of possible universes allowed by string theory could be more than 10^500 TT. To put that in perspective, that's more than the number of atoms in the observable universe. If even a tiny fraction of those universes are viable, the implications are staggering. We're not just living in a universe, we might be living in one universe out of an unimaginable sea of possibilities. This is where string theory begins to challenge not only our understanding of physics, but our place in existence. Are we special? Or are we a random fluke in an infinite multiverse? Could other versions of us exist in universes governed by slightly different physics? Could there be realms where gravity is stronger, time flows differently, or stars never formed at all? String theory doesn't just offer new physics, it offers new philosophies. Some physicists embrace the multiverse. They argue that just as Earth isn't the center of the solar system, and the solar system isn't the center of the galaxy, our universe might not be central in the grander cosmic structure. We are one bubble in a vast cosmic foam. Others resist. They argue that if we can't test or observe these other universes, then this isn't science, it's speculation. Without empirical evidence, how can we be sure that string theory is describing reality and not just an elegant mathematical mirage? And yet, string theory continues to influence nearly every branch of theoretical physics. It has given rise to powerful tools like the ADS-CFT correspondence, a mathematical duality that suggests a surprising link between theories of gravity in higher dimensions and quantum field theories without gravity in lower dimensions. This holographic principle could one day help us solve black hole paradoxes, understand quantum gravity, or even uncover the quantum nature of space-time itself. But beyond the math, beyond the equations, string theory forces us to reimagine the very fabric of existence. In classical physics, reality is composed of point particles, tiny dots that collide, bounce, and interact in predictable ways. But in string theory, these dots are replaced by loops, vibrating, twisting strands of energy, each with its own frequency, like the strings of a violin. And the universe itself? It becomes a vast, multi-dimensional concert hall filled with the harmonics of creation. This perspective opens new doors, not just in science, but in how we see ourselves. If everything is made of vibrating strings, then so are we. Our bodies, our thoughts, our very essence resonate with the same symphony as stars and galaxies. We are not observers standing outside the universe. We are the universe experiencing itself in human form. So what does this mean for the future? If string theory is correct, It could revolutionize our understanding of everything from the birth of the universe to the structure of black holes. It might explain the mystery of dark energy or provide the key to quantum gravity. It could help us build a theory of everything, a final, elegant equation that describes the entire cosmos in a single breath. But even if it doesn't, even if string theory turns out to be wrong, it has already given us something priceless, a new way of thinking, a new way of asking questions, a reminder that reality may be far more beautiful, strange, and interconnected than we ever imagined. And in that pursuit, in that willingness to imagine a universe of 10 dimensions, vibrating energy, and hidden symmetries, we expand the boundaries of what it means to be human. Because to explore string theory isn't just to study physics. It's to listen for the music of the cosmos. Despite its elegance, string theory faces one major challenge. It has yet to make a single testable prediction that can be confirmed by experiment. In science, a theory gains strength when it can be proven right or wrong through observation. General relativity predicted the bending of light around stars. Quantum mechanics predicted the existence of particles later discovered in laboratories. But string theory, its predictions exist at energy scales so high, they are far beyond the reach of our most powerful machines. This has led some physicists to accuse string theory of being unscientific, beautiful mathematics but without physical consequences. If we can never test it, how do we know it's true? Can a theory still be considered science if it lives entirely on paper? Proponents argue that string theory has already delivered value, not through direct predictions, but through the insights it has generated. Tools developed within string theory are being used in quantum computing, condensed matter physics, and the study of black holes. The theory has helped bridge disciplines, offering connections between gravity and quantum mechanics that had long seemed impossible to reconcile. And then there's the question of uniqueness. In traditional physics, a good theory leads to a single universe, one set of rules, one consistent reality. But string theory, with its string landscape of possible solutions, implies that many, maybe even infinite versions of reality are possible. This idea is deeply unsettling for some scientists. If everything is possible, then how do we explain why our universe looks the way it does? This brings us back to the anthropic principle, the idea that the universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. In other words, we live in a universe that supports life simply because only such universes can be observed by beings like us. Is this a satisfying explanation? Or is it a retreat from deeper understanding? Some physicists see this line of reasoning as a philosophical dead end. Others see it as the best answer we have, given the current limits of technology and observation. And some believe that one day, string theory will make a breakthrough, perhaps through unexpected connections or entirely new physics beyond our current grasp. One possible future lies in the development of quantum gravity, a theory that combines general relativity with quantum mechanics. String theory is one of the most promising candidates for such a unification, offering hope that we might one day understand what happens at the heart of black holes, or what existed before the Big Bang. Another possibility is the use of quantum computers to simulate aspects of string theory that are currently impossible to test in the real world. As our computational power grows, so does our ability to explore theoretical models with incredible complexity. And who knows? Just as Einstein once had to wait for new telescopes to confirm the predictions of relativity, maybe string theory will simply require a leap in technology, something we haven't built yet or even imagined. In the meantime, string theory challenges us to think differently, to stretch our imagination, to consider the possibility that the universe is not made of particles, but of tiny vibrating loops of energy, that everything, light, gravity, matter, and even space itself, is the result of invisible strings dancing through a 10-dimensional stage. Whether true or not, string theory has already transformed physics. It has taught us humility, showing how little we know. It has inspired unity, bringing together the best minds from different disciplines. And it has invited wonder, reminding us that the universe may be more strange and beautiful than any story we've told before. In this journey, the goal is not just answers, it is understanding. And understanding, as always, begins with curiosity. In the end, string theory remains a bold attempt to answer some of the deepest questions in science. Is it the ultimate theory of everything? Maybe, maybe not. But its pursuit reminds us that the universe still holds countless mysteries, and that the journey to understand them is just as important as the destination. Whether or not strings are the fundamental fabric of reality, one thing is certain: our quest to comprehend the cosmos is far from over.